So guys, Simon Ritter on Java 2024. Simon, stage is yours.
Right, great, thank you very much. Yes, so as I said before the session started, we're looking at how to, as the title says, keeping your Java hot by solving the JVM warm-up problem. And the reality is that if we look at what happens when you start a Java application, there's actually several different parts to it. And we can look at the effect that that has on performance and what we might be able to do to change that, to improve the performance. So the first thing we can see is that in terms of starting a Java application, you have to start the JVM. JVM itself is an application, so that's written in C++, compiled into native instructions. So you start it as you would any native application on a particular platform. That needs to do certain things. So it needs to load and initialize the JVM itself. But then there's one other thing that's kind of interesting that the JVM does when it starts up. It does this every single time it starts up, is that for each bytecode in the instruction set that the JVM has, it will generate a template for that bytecode, which is a set of native instructions. And the idea behind this is that if you start your JVM on a particular platform which has a particular microarchitecture of the CPU, then it can take advantage of whatever the facilities are of that particular platform and can tune things, if you like, a little bit to try and get better performance. Not really going to make a lot of difference, as we'll see, but it's the idea that at least you can get a little bit more performance from that. So that's starting the JVM itself. Then you need to start the application code for your bytecodes. And that involves doing various things like loading the classes that you have for your application. Then you've got to load the class which has the main entry point in it. Then you need to initialize the application classes. So that's doing static initialization, calling constructor where it's necessary, and so on. And that will then get you to the point where you've got your Java code loaded and ready to actually do something. But then there's still more to it than that, because of course you've got application-specific initialization, which is what you do in your application. So in your application, you might be opening a connection to a database, you might be opening a connection to a network or something like that. And that needs to be handled before you can start doing the real work of the application. Once we've done that, then we get into this application warm-up kind of idea. And that goes through various different things as well. So as I said, what we'll see is that we'll start interpreting our bytecodes, and then over time, the JVM will keep track of how many times each method is called. And when we hit a certain threshold for a particular method, it will decide that that's a hotspot of code. And so it will compile it into native instructions. And that happens in a number of different ways, which we'll talk about as we go through. We can also have what are called de-optimizations, and I'll kind of come back to that later on as well, and then recompilations. And all of this work is something that happens whilst your application is running. And that can have different impacts on performance, because clearly there's one impact, which is the fact that as you're starting your application, it's all running in interpreted mode. So that will be a lot slower than if you've got heavily optimized code. But it's also the impact that doing that compilation using the same CPU, the same memory that's being used by your application will, again, degrade the performance of your application. Plus, you've got the application itself having to do specific workloads and so on at the same time. Now, if we look at this in a bit more detail, we can see that the time to get into the first operation where your application can do some useful work is the combination of starting up the JVM itself and starting up the application. We can see that the time it takes to complete N operations, so the overall workload of our application, is the combination of all three of those things. The other thing we can look at is how much effect we can have in terms of improving the way that the application works. So if we look at the JVM startup, that's fast. I mean, it's literally the order of like a few, maybe tens of milliseconds. So even if we improve that by, let's say, 100%, if we halve the time that it takes to do that, we're still only going to be talking about a few milliseconds in terms of improvement. Not really much point in focusing on that. Application startup is quick. So loading application classes, initializing application classes, and so on, that happens fairly quickly. The time it takes us to get to our main entry point where we can do some useful work is normally pretty quick. The application warm-up time, though, is something that can take a long time. Depending on what the profile of your application is, it can take minutes, it could take hours to find all of those hotspots of code, compile them, recompile them, figure out all the optimizations that are needed, and so on. So it can take quite a long time for that application warm-up to occur. So let's just talk a little bit more about that performance warm-up again. So as I said, class files, bytecodes, instructions for our virtual machine. So we interpret those, and then the compiler, the JIT compiler, will identify those hotspots of code, and it will compile them. But it does that in more than one phase. So we've got a just-in-time compiler, but we've actually got two of those. The first of those, very imaginatively named C1, is designed to compile code as quickly as possible, but doesn't do a lot of optimization to that code. The idea being that when we use C1, we want to generate some code, be able to run it as quickly as possible, but then we'll profile how that code is actually being used as the application runs. When we've got to another threshold in terms of how frequently that method is called, we can then recompile the code using, again, the imaginatively named C2 JIT compiler. What the C2 JIT compiler will do is it will take longer to compile the code, but it will use all the profiling information that's being collected whilst we're running under C1 compiled code and generate much more heavily optimized code. So this then gives us better performance overall for our application. Now, the drawback to this is that when you start your application, it will go through the process of identifying these methods that need to be compiled. It will use the C1 JIT compiler, profile the data, then it will recompile with C2. Great. When you restart the application again, it has to do everything from scratch. There is no memory of anything that's happened before. So it goes through exactly the same process of identifying the same methods, compiling it with C1, profiling, recompiling with C2, and so on. And that, if you like, is very inefficient. So what we'd like to be able to do is to improve the way that we can do that. Now, if we look at a sort of a generic performance graph, this is typically what we're going to see. So I say typically, this won't be all particular applications, but we can see here that we've got, in terms of performance, on the left-hand side, when you start your application, it's running slowly. And that's the sort of yellow bit that you can see there, where it's running in interpreted mode. As we compile methods with C1, we'll see the green code, and it gradually sort of improves performance. And then we get into the blue area, which is where the C2 compiled code is being used. So the application warm-up is the length of time that it takes to get to where we've got our optimum level of performance. And you'll also see that there are various dips in performance as we go through that graph. There are some fairly big ones in the sloped part, and then there are some fairly regular dips that we see once we've got to that optimum level of performance. And those occur for different reasons. The ones, once we've compiled our code and we've got to our optimum level of performance, is all about garbage collection. So if we're using a garbage collector that needs to pause the application threads, we'll see dips in performance. More modern garbage collectors are more concurrent, less pausing, so we'll see less of those with modern GC algorithms. But we'll also see these big dips in the graph as we warm up, and that's due to what are called de-optimizations, which I'll explain in a moment. So as I said, the problem that we face is that when we run our application for the first time, we will see this kind of graph. When we run the application a second time, we see exactly the same thing. We're going through the same process of identifying the methods, compiling, recompiling, and so on. Same warm-up shape to the graph. And if we run it a third time, we'll see the same thing. And that can happen again and again and again. What we'd really like is something like this, where we run our application, we let it warm up, we get to a steady state in terms of our performance, but then when we run it again, what we want is to pick up from the point where we left off. So we have some memory of what has happened, and we can reuse the compiled code from a previous run of our application, and therefore have that optimum level of performance right from the very beginning and continue for the whole lifetime of the application. And if we started at a third or subsequent time, then we get exactly the same thing. So that's really our ideal compared to what we're seeing in reality. So there are a number of different solutions that we can apply to this. And what I'm going to do is I'm going to talk through each of these solutions and give you the sort of pros and the cons, the advantages and the disadvantages of each, and where you might want to apply these techniques to change the performance profile of your application, depending on what your application does. So the first solution is ahead of time compilation. And I remember that when we first started developing Java, I was at Sun back in the mid-90s. And one of the sort of problems we had with early versions of Java was it was very slow compared to C or C++ natively compiled code. And a lot of people suggested, well, the simple answer is to avoid using the Java virtual machine. What we'll do is we'll simply take the Java code in the same way that we do C++, compile it directly into native instructions, and run it on the machine to get good performance. So this is one possible solution. So let's look at what that really means. So this is, again, the traditional approach, ahead of time static compilation. What we're doing is we're saying, take the Java code, treat it just as we would other forms of source code, and rather than compiling it into bytecodes, we compile it directly into native code. This is good because we don't have to interpret any of the bytecodes, so we can eliminate that whole section of our performance profile. It also means we don't have to do any analysis of hotspots as we're running our code. We don't have to do compilation of the code whilst we're running the application, which also reduces that load on the CPU, meaning that we've got more resources available to run the application because we're not having to share the CPU between doing the work of the application and compiling the code at the same time. The other benefit is that we start right away at full speed and we don't have to go through this warm-up effect. So this is the approach that Graal native image takes. So Graal is a project that's been around for a long time now. Again, it was started back in the Sun days, where it was one of the Sun Research Labs projects as a kind of combination of different things with the Graal native image, the idea of the substrate JVM, the truffle framework for other languages and so on. And there's another OpenJDK JET that's being used to explore some similar approaches to using that within OpenJDK. So Graal native image is about taking Java code and compiling it directly into native instructions. Wonderful. So at this point, I can just say, well, we've solved the problem. We've eliminated all the issues that we've seen in those graphs that I talked about. We no longer have to do all of this work. So surely this is the perfect solution for everything. We just compile our code before we run it and off we go. Except not so fast. And I mean that in two different ways. So not so fast in terms of this is the solution to the problem, but I also mean not so fast in terms of the code that we generate for our statically compiled code. Because ahead of time code is by definition static, statically compiled code. That means it does not change. We compile it before we use it. Using the compiler, everything is created in terms of the native instructions, sequence of instructions that we need, and that does not change. The other important thing is that the code is compiled before it is run, very logically, because it's ahead of time compilation. So if it's compiled before it's run, then that means that we don't have any knowledge of what the code is actually going to do when it's running. So we have to make assumptions about the way that the code has been written, the structure of the code, and what we can do in terms of optimizing it for a particular application. So this is the idea where when I talked about C1 and C2, C1 generates some compiled code, but then it profiles the application as it's running. And that profiling information is then fed into the C2 JIT compiler to then optimize the code based on what the code is actually doing as it's being run. Now, there's another technique which has been around really since the beginning of compilers, which is called profile-guided optimization. The idea behind that is that you compile your code statically without any assumptions about what the code is actually going to do. You then run your application with a representative workload, you run it in production, get people to interact with it in the way that they would normally do so, and you profile that. That generates a set of profiling information to tell you what the code is actually doing. Feed that back into the static compiler, recompile the code, now using the profile you've generated, and generate a new set of instructions, given that you have now some knowledge about what might happen when you run the application. But this only helps partially, because we still have the issue that when the application is running, people may do different things. There may be different interactions, there may be a different set of data that's processed, and that can lead to very different profiles or paths through the application code, which leads to very differing interactions, so that we need different code to run that. Now, let's look at in a bit more detail about what the JIT compiler can actually do to improve performance. And what we have are things called speculative optimizations. And the idea behind a speculative optimization is that you're saying, I've profiled the code the way that it's running at the moment, and I have discovered a certain set of things that I believe to be true, because they've been true up until this point. Let's assume that those assumptions will hold for the rest of the time that the application runs. And we'll use these speculative things to help optimize our code. So let's look at a couple of examples of this. The first is what we call inlining of a monomorphic site. Sounds kind of complicated, but it's not really. I have here a class which is called animal. And in that, I've got some state, which is a color. It's a private variable, private instance field, so we can't access it directly. To get to it, we need an accessor method, a get method. So I've created a get color method, which returns the color. And when I write my code and I say, okay, I've got an object of type animal, I've got some data in there, and I want to get the color of the animal, I can do it by simply calling animal.getColor. Great. But of course, what this is actually doing, if you look at the compiled code underneath, is the compiler is having to say, right, we're calling the getColor method, which requires us to create a stack frame. We put the stack frame on, we call the getColor method, we execute it. All that's going to do is find the value of the color in the object and return it through the stack frame. We then pop the stack frame off and we get our result. That is very inefficient because, of course, we're creating a new stack frame every time, even though all we're doing is returning the color. So what the compiler will do is it will analyze that and say, okay, I don't need to actually do that. Because I can see that the getColor method is only going to return the color value, what I will do is I will treat the private instance field as if it's public. And the compiler can do that because it's quite safe. There's nothing that it's doing here that will break the contract between what we've written in our code and what the compiler is actually generating. So it effectively changes the code underneath to make sure that we can get better performance from the application by avoiding this overhead of having a stack frame and then having to pop the stack frame off. But here's the key thing. This will only work if we know that there's one implementation of getColor. Now, Java is not a dynamically typed language, but it is dynamic from the point of view of being able to load classes at runtime. So we could load at runtime a new version of the animal class, which maybe does something different in terms of getColor. At that point, the assumption we've made about the ability to treat the color instance field as if it is public would potentially be invalid. And so we couldn't then use that code and we'd have to do something different with that stack frame and so on. So that would then mean we'd have to throw away the code that we had created and recompile the code to take account of a different implementation of getColor. So that's what I refer to when I say about de-optimization. This idea that we've made an assumption about the way the code works. Somebody has now loaded a new animal class, changes the way the code works. We have to throw away that compiled code and then replace it. But this speculative optimization can be a lot more complex. And so I've got an example here, which is what we call branch analysis. In this case, I've created a slightly convoluted, contrived example, but it's very good to show what we can potentially do in terms of speculative optimizations. So here I've got a method called compute magnitude, takes a value as a parameter. And then we do a test, see, is the value greater than 9? If it is, we call a separate method somewhere else, compute bias, passing in the value. If the value is not greater than 9, we set the bias equal to 1. And then we're going to return the log base 10 of whatever the bias is plus 99. Branch analysis says, let's count how many times we go through the true branch and how many times we go through the false branch. When we come to compile this code, we can look at those values and the compiler can say, okay, so far in running this application, we have never had a value that is greater than 9. We've only had values of 9 or less, which means we've only ever set the bias to be 1 and then return that. So the compiler can then be quite sophisticated in terms of what it can do to change the code. And it can actually do this. So it can say, right, compute magnitude method, still passing in value. But now we have a slightly different way of doing things. We say, if the value is greater than 9, then we call this method called uncommon trap. The reason for that is that although we've made the assumption that the value is never going to be greater than 9 because that's the way it has worked up until now, because we have a contract between the compiler and our code, we still have to deal with the fact that a value may be greater than 9 at some point in the future. If it is, uncommon trap is calling down to the compiler and saying, this code is now invalid, we must throw it away, and we must go back to the code that we had for the full method that we saw on the previous slide. However, if we don't get to that point, if we still have values which are 9 or less, then we can simplify the code a lot because we know the bias is going to be 1, 1 plus 99 is 100, log base 10 of 100 is 2. So let's avoid all of that work and simply return 2 every time. So this will work so long as we don't get a value which is greater than 9, resulting in a de-optimization. So speculative optimizations are very, very important for performance in terms of the JVM. And at Azul, what we've done is we've monitored this, we've measured it, and we find that realistically over 50% of the performance gains that we have from using a JIT compiler are due to speculative optimizations. So as I say, they're very important in terms of getting that high level of performance from your application. But obviously, they only work if you can de-optimize when an assumption that you've made proves to be false, and you then can throw away the code and recompile it. Now, the other thing to understand is that de-optimizations are extremely bad for performance. So we'd like to try and avoid those as much as possible. The reason being that obviously, if we've already compiled optimized code for a particular method, and then our assumption proves to be wrong, we have to throw that code away, and then we have to recompile the method again with a new set of assumptions, which takes lots of CPU cycles. So it's really doubling the amount of work that we have to do for that method. So very much in terms of the performance, we don't want to see the optimizations as much as possible. So if we compare ahead of time compilation with JIT compilation, we can see that obviously for ahead of time compilation, we can say that class loading prevents us from doing very aggressive method inlining because we can't guarantee that at runtime there might not be some class that's being loaded. So we have to get around that. We can't generate bytecodes at runtime, so that's a limitation on what we can do. Reflection becomes complicated with ahead of time compilation. You look at the way that Graal VM works, you have to really declare all of the reflection that you expect to use in order to have that handled by the Graal JIT compiler. You can't use speculative optimizations in AOT because obviously you're not profiling the code as it's run. You can use profile guided optimization, but that's very different to using speculative optimization. So overall, performance will typically, and that's not every case, but typically be slightly lower because we can't use some of the techniques we can use for JIT compilation. But obviously the benefits are full speed from the start and no CPU overhead to compile the code at runtime. JIT compilation is essentially the opposite of all that. So we can use aggressive method inlining because we know exactly what method is being called at any given point when the code is running. We can use runtime bytecode generation because we're using bytecodes. Reflection is, and I put in brackets, relatively simple because I don't think anybody really thinks reflection is ever simple. You can use speculative optimization, and overall, your performance will typically be slightly higher. Obviously, the downside, as we've already seen, it requires warm-up time, and you place an additional load on the CPU, so you've got an overhead to compile the code at runtime. So again, if we go back to our typical graph and we look at that, we can say, right, with JIT compiled code, we go through the warm-up, we see the performance gradually improve until we get our steady state. If we compare that to ahead of time natively generated code, what we're going to see is very fast startup, but at a slightly lower level. Even if we use profile guided optimization, which will improve things further, because we can't compile code at runtime knowing exactly what is going on, we're never going to get to that same level of performance that we will do overall with JIT compiled code. So it's interesting to see that there are different levels of performance that we get, even though we have slightly better, have a lot better in terms of the startup and the warm-up. So when to use ahead of time compilation? Really, I mean, there are some very good examples where we can do that. So ephemeral microservices, or what people insist on calling serverless computing, AWS lambdas, that kind of thing, where you've got very short-lived services which basically are starting up, doing something, and then shutting down immediately. Then startup and warm-up time is much more important than the overall speed you're going to get. Garbage collection, usually a non-issue with those kinds of things because they're very quick. Also, if you're running microservices where you have resource-constrained containers, let's say you've got a 2 vCore container, then what you'll find is that for things like that, the JIT compilation as you're doing warm-up is going to significantly reduce the throughput that you get during warm-up. Because essentially what's going to happen is one of those vCores is going to be doing application code, one of those vCores is going to be compiling your code. That means you've reduced the amount of throughput that you can get by 50% by having one of those vCores doing your compilation. So there definitely are some very good situations where AOT makes a lot of sense, Graal VM. Okay, what about solution number 2? What about if we store some or all of the JIT compilation data? Okay, so this is a piece of technology that we've developed at Azul in terms of our Prime VM. So we have Azul Prime as a product, and what this allows us to do is to say, okay, let's run the application until it's warmed up. So training run, same thing you would do with profile guided optimization. Run it till it's warmed up, and then we will take a profile of the running application. And that profile consists of basically 5 pieces of information. Firstly, all the classes that are currently loaded. Secondly, all the classes that are currently initialized, because that could be a subset of the loaded classes. Maybe not all the classes that you've loaded have actually been initialized yet. We'll take a copy of all the profiling data that has been collected whilst the JIT compiler has been doing its work. So that profiling data that was collected whilst we were running C1 generated code, then we'll keep all of that. And the other important thing we'll take is also any de-optimizations that happened whilst we were doing that warm-up. So any mistakes we made in terms of our speculative optimizations, we'll keep a detail about that so that we can avoid that problem in the future. And then we'll also take a copy of all the compiled code that was generated by the JIT compiler. When you restart your application, we will take that profile as input to the JVM along with the jar files and classes that you need for your application. The JVM can then say to itself, right, I know which classes I need to load, I know which classes I need to initialize, because that's the ones that were in the profile that was collected. So we'll do all of that work ahead of time. We'll then load the code if we can. So if we're running on the same architecture, even to the microarchitecture level, then we can reuse the compiled code. Or if we're not running on maybe the same microarchitecture or a different set of CPU or whatever, then we can actually compile methods we know we're going to need, using the profiling information that was collected, so we can generate that heavily optimized code straight away. And we do all of that work before we get to the main entry point. What that allows us to do is to really change the graph that we have. So if we simplify our warm-up graph and we look at it without ready now, then we're going to see this gradual slope, get to our optimized level, and then run the application with our optimized code. If we look at what we get with ready now, we see a different profile to the graph. So now we've got a much steeper warm-up graph because all of this work is being done ahead of time. We know what we need to do. We can get to that optimized state much more quickly and then deliver that optimized level of performance for almost all of the time the application is running. Now, if you look carefully at this graph, you might see there's a little bit of a problem with this. A little bit of the problem is that there's a period of time where the application is not doing anything. So this is time to first transaction. So the time to first transaction is going to be longer using ready now because we have to do all of the class loading, have to do the initialization, potentially have to do compilation before we get to the main entry point. So that's essentially dead time before the application can do its work. Now, in certain situations, that's not really a problem. If you're running something like a trading application and you know that the trading day starts at 9 o'clock in the morning, then that's fine because what you can do is you can say, right, we'll start our application at, say, 10 to 9. It can go through all of the class loading, initialization, compiling, and so on, and then it's ready to go at 9 o'clock with the full level of performance. Now, Project Leiden is an OpenJDK project. So I just talked about what we do at Azul with our platform Prime. Project Leiden, as I say, is part of OpenJDK. And this has been a project that's been around for probably 2.5, maybe 3 years now, with the goal of improving startup and warm-up time. What they've come up with so far are a number of different things. 3 specific things. First of those is the idea of AOT class loading and linking. So this is related to what's called application class data sharing. This is a thing that was introduced quite a long time ago in Java and became part of the OpenJDK in, I think it was JDK 11 that was contributed. What application class data sharing does is it says, right, when you run your application, you will load classes and you will initialize classes. And there are a set of data structures internally in the JVM that need to be created as those classes are loaded and as those classes are initialized. Obviously, again, every time you start up the application, the same thing has to happen in terms of it has to do the class loading, the class initialization. So what AppCDS does is to say, okay, once you've loaded your classes, initialized them, we have those data structures in the JVM's memory. Let's create a file that contains those data structures as a binary data. When you want to restart your application, what can happen is that rather than having to go through the process of class loading and class initialization, we can simply take that binary file that we've created previously, memory map it into the JVM's address space, point the JVM at that particular area and say, this is where the class information is. All those data structures are ready to go. So it reduces the amount of time that's taken to actually get your classes loaded and initialized. This gives you, there's some other things that are being done in this JET, so it's worth reading JET 483, but that's the basis of it, is to reduce the amount of time it takes to do various housekeeping activities that the JVM does when it loads your classes at the beginning. Second thing is ahead of time method profiling. So what they're going to do is they're going to cache profiling data from a training run. So get to a point where you've got your application running, collect the data about the method profiling, which is used for the JIT compiler, and then when you restart the application, you can reuse that information again. And similarly, ahead of time code compilation. So caching the compiled code from a training run, reuse it when the application restarts. Now, the process that they use for this is actually currently 3 different phases. So there's a training run where you collect that information, then there's an assembly phase, and then there's a deployment run. So it's a little bit more involved than what I explained in terms of Platform Prime, but it does essentially the same thing, because all of this sounds very familiar because it's exactly what I just talked about, what we've done at Azul. So they kind of used similar ideas to what we did with our product, and now they're including it into the OpenJDK. Okay, solution number 3 to improving the way that the performance of our warm-up can work. What about if we decouple the JIT compiler? Right, let's look in a little bit of detail at the architecture of the Java virtual machine. So there are distinct areas of that which do different things. So the area in green is all about class loading subsystem, where you load classes, you do the verification, make sure that there are no illegal sequences of bytecodes, you do the linking of the bytecodes and so on, initialization of the code and all that sort of good stuff. Then you've got the runtime data area. So you've got the data for the methods, you've got the heap that we're aware of, where you keep all your data, you've got the stacks for the different threads in your application, and then you've also got native stacks and memory for the JVM itself. Then you've got the blue area, which is the execution engine, the thing that does all of the work of the application through the JVM. So you've got the interpreter, which takes your bytecodes, does the interpreting using these templates. You've got the JIT compilers that we know about, C1 and C2, that will compile code as it's running, garbage collector, which does the memory management for you, and then obviously you've got interaction with native code through JNI or native method libraries. Now, if we look at that in detail, there's one particular area that we could improve performance in terms of warm-up, and that's the JIT compilers. So what we decided to do, again, in terms of looking at how we can improve things, is say, okay, let's take our speculatively optimized code and let's turn that into a unit. And a unit, in this sense, is the actual optimized code that we have for that method, but we'll also combine that with a set of assumptions that we used to compile that code. So this is the idea of those speculative optimizations. So we could take our methods that we had and we could say, right, we've compiled this with the assumption that there will only be one getColor method that we had previously, and we'll say that the value is less than 10. But yes, less than 10. So we know that that code will work if these two things are true. So that gives us essentially a method that's been compiled with a set of assumptions. Now, the other thing that we need to understand is, as we've already kind of explained, is that JIT compilation has cost. The fact that we have to do the compilation whilst the application is running means that we're using the resources of the underlying machine at the same time that we're trying to do the application code. The thing about that is that we have to compromise on what we do, because JIT compilation you can take to different levels. So in terms of the optimizations that you can apply, you can say, right, well, we can do these types of optimizations. They're not too heavy in terms of the amount of CPU that they require. Or we could do other more heavy optimizations, take longer to process, longer to actually generate the code that we need, but will give us better overall results. So the compromise is, how much do we want to spend time using the resources that we've got, the limited resources we've got, versus the level of optimization that we get from the application. So if we're running on a nice big powerful machine, we've got 64 vCores and 64 gigabytes of memory, then probably we can really kind of optimize quite heavily because we get lots of resources to be able to use. But if you're in a 2 vCore container with 2 gigabytes of RAM, then heavily trying to optimize the JIT-compiled code is going to give you very heavy degradation, because again, 50% of the resources are going to be dedicated to using the JIT compiler. But we can also get even bigger problems than that, because with only 2 gigabytes of memory, if we've got a memory hungry application and then we're trying to do heavy optimizations at the same time, we can end up with an out of memory error. Even though the application is not running out of memory, the container itself is running out of memory. As I say, what we end up with is compromise in terms of how much we can optimize versus the amount of memory and cores we need. So if we look at a graph here, so this is looking at a 2 vCore container. What we can see here is that the graph on the top is the throughput over time. So we've got a nice steep graph where we're warming up, fairly simple application, presumably warms up quickly, gives us our steady state overall performance. The graph at the bottom is showing CPU utilization. And because we've got a 2 vCore container, what we're seeing is as we compile the code, we're using both CPUs, so we're thrashing both CPU cores. Then once we've done the compilation, we drop down and we're really running on 1 vCore. So we might, if we could avoid the compilation, we might even be able to get away with using a smaller container. Now, if we overlay that with the blue graph here, what this is showing is if we try and apply more heavy optimization. So the orange line is essentially hotspot using the C2 JIT compiler. The blue line is where at Azul, we use a different JIT compiler called Falcon. It's based on another open source project called LLVM. What this does is have a very different profile to the one we see in orange. Clearly, top graph, which is throughput, shows that we warm up much more slowly, but we also see significant dips for quite a long time, which is where we're seeing more heavy de-optimizations. That's because we're doing more speculative optimizations, more use of that, and sometimes those assumptions prove to be wrong, so we have to back out the code and then recompile it. But the good thing is, you look at the right-hand side of that graph, is that the blue line is significantly higher than the orange line, meaning that the overall throughput that we get once we've warmed up is, in this case, maybe 20% higher than if we just use the orange line using the C2 JIT compiler. Again, if we look at the lower graph, we can see that the impact on the CPU is much more marked. We're having to do a lot more work in terms of CPU to compile that code. There's a lot longer that we see the heavy use of the CPU cores, recompilation, and so on. So this is showing us that we can have a better overall performance, but the warm-up time is affected. So what we said is, okay, how about if we decouple the JIT compiler from the JVM? Lots of people now are running in the cloud. Even if you're not running in the cloud, you're running in your data center. Why not assume that if you're running in the cloud, that you have access to almost infinite resources? So let's take the JIT compiler out of all of our individual JVMs using a microservice architecture, lots of different services. Let's effectively remove the JIT compiler and make it into a centralized service that all those JVMs can use and all those JVMs can share. This is what we call the cloud native compiler. So now what happens is when a JVM needs to compile code, rather than doing it locally, it takes the method that it needs to compile with the profiling data, sends it as a message to the cloud native compiler, has that do the compilation for it, gets it back across the network, and off it goes. What we then see is a difference in terms of our graph. So going back to the comparison between the orange line, which is C2 JIT compiler from hotspot, and the blue line, which is the Falcon JIT compiler in prime JVM. As I say, what we see is that overall we get better performance at the end, but we have a much slower and more varied warm-up. Now let's overlay this with using the cloud native compiler. And what we can see here is a green line. So the green line is saying, let's use the cloud native compiler, not do our JIT compilation locally. And if I just drop the blue line out to make that a little bit clearer, now what we can see is that the green line is very much the same as the orange line in terms of that speed of warm-up, and we get to that optimized level of performance much, much more quickly. So it takes only a short space of time before we get to that 20% higher level of performance. And then the other great thing is that on the lower graph, we can see that there's now almost no impact from the JIT, well, there will be no impact from the JIT compiler, but the amount of time that we need to use both cores is, again, significantly reduced, so we can get more throughput for our application because now we're not having to load the CPU to do the JIT compilation locally. So this gives us a much better performance graph in terms of the effects that we can get. So a lot of people will say, well, isn't this just shifting the cost? Well, yes, it is, but we're shifting it to a much more efficient place. What we can do is we can set up a cloud native compiler with more resources so that we can do these heavy optimizations, but we can do them in different ways, meaning that we could say, right, so when a method is called, when a method is passed into the cloud native compiler, what we'll do is compile that with a level of optimization, which gives us results fairly quickly. Pass that back to the caller, and it runs its application. Great. But when we can also do is, because we can run in the background, in effect, we can then recompile that method using these more heavy optimizations, which take longer. The next time the method is requested, then we can simply say, right, it gives you the heavily optimized code. So then you get even better performance from that. And we could even preemptively do that by saying, okay, now we have a new version available, tell the JVM that it's available and can then use that. The other thing is that because the cloud native compiler runs all the time, or effectively all the time, we can then say, right, rather than having to compile those methods every time that we need them, we can cache all of that. So if we're running multiple instances of the same service, every time they ask for a method that we've already compiled with the same set of assumptions, then we can simply run that and provide it to the JVM straight away. So again, it improves the efficiency. And as I say, we can actually have different compilation for the same method. So we have the same method will be compiled based on different set of assumptions, different set of speculative optimizations. So we know we can match against that and then deliver the right piece of code with the right optimizations for that particular situation. Solution number 4. So what we can do here is combine solution number 2 and solution number 3. So this is what we call the Ready Now orchestrator. Realistically, all this is doing is saying, okay, we'll have the cloud native compiler, but we'll also keep the Ready Now profiles as part of that, so that you can then combine the two things, have your cloud native compiler, have your Ready Now information about which classes need to be loaded, which classes need to be initialized, and so on. And that, again, is doing very much the same sort of work that the Project Leiden is looking at doing. Okay, solution number 5, last one I want to talk about here, is what about if we save the whole application state? Right, so if you look at Linux, Linux has this thing called CRaU, C-R-I-U, and that stands for Coordinated Resume in User Space. It's been around for quite a while, and it's essentially the same idea that if you are running on your laptop and you've got a file open, you're editing a word processing document, you've got a web page open and so on, when you close the lid, your laptop stops doing things. When you open the lid of your laptop, it goes back to exactly where you were before. So you can continue editing your file from the same place, you can read the web page from where you left off, and all of those sorts of things. So the idea behind CRaU is to take the same sort of approach as closing the lid of your laptop to a running application on a Linux machine. And the state that it stores is in user space. So it's just a set of files that it stores the data in. You can think of it kind of like the idea that in a time-sharing operating system, the way that you used to get around having only a single CPU was to very quickly change between processes. And you would do that by saving the state of the process. You'd have the CPU, you'd have the program counter, the registers, all of that information, and you'd swap that in, swap it out very quickly to give the illusion of more than one thing running at the same time. So this is essentially doing the same thing. It's rather than storing it into memory, it stores it into a set of files. Those files can then be reloaded again. They can even be moved to a different machine and used multiple times if you want to. So what we did was we said, okay, let's build something on top of that for the JVM, because JVM is essentially just a process. So we could use CRaU and we can checkpoint the JVM. But we need to be a bit more careful than that. So we decided we would call this Coordinated Restore at Checkpoint, or CRaC. The key thing here is that we want to make the application aware that it's being checkpointed and aware that it's being restored. So we have our application running and we decide we want to do a checkpoint. So we tell the application that we're going to create a checkpoint, and then we create that. So the application is able to take certain action that it requires to safely create a checkpoint. I'll talk about that in a moment. Then we can keep that state for a while, and at some later time, we can make the application aware that it's being restored, so it can do certain things it needs to do, and then it can continue running from that exact same point. So effectively closing the lid on the laptop, opening it up again. What we do is we enforce more restrictions on a checkpointed application than CRaC will. So CRaC will try to store all of the state of the application and then just restore it once it's running. This can be very difficult because if you've got things like files open, if you've got database connections, network connections, you close. If you simply do a checkpoint on that and then try and restore those again at some point later, there's all sorts of problems in terms of the stale file handles, the database connection may have timed out, various things like that. So what we do is we enforce the idea that you can't have any open files or sockets. And that's what the checkpoint must do when the application is running. It must say, okay, the application now knows it's about to be checkpointed, close all the files that you have, the database connections, the network connections, and so on. And then when you restart the application, you can reopen those files, reopen the network connection, start up the database connection, and so on. And you can even do more sophisticated things by saying, okay, I'm closing this file. Let's do a checksum on the file so that when we restart the application and do a restore, we can not just open the file again, but we can also check whether the file has changed since we last saw it. If it has, we can then maybe reread the data or do something different with that. So it gives you the ability to be more flexible. Now, the way this works is very simple. We have created a basic API that you use in your application. And it all revolves around the idea of a resource. Resource is an interface with two very imaginatively named methods, before checkpoint and after restore. So where you have a class which needs to be made aware of a checkpoint and a restore, you implement this interface. You have two methods that you need to implement. Before checkpoint is where you close your files, maybe do the checksum. After restore is where you then reopen the file, check the checksum, see if it's changed, and so on. So this is where you can do the work you need to do before the checkpoint happens and after the restore happens. When we want to be able to use that, what we do is we say, okay, we've got these resources, so classes which implement this interface. They must then register themselves with the JVM so that the JVM knows which classes need to have the before checkpoint and after restore methods called. So you register through a context. There's a global context for the JVM itself, or you can create your own if you really want to, but most people are just going to use the global context. Register your resources, and then when you do a checkpoint and a restore, all the methods are called by the JVM and everything happens in the way that you want it to. The other thing that's important about this is the order in which things happen. So you can register your resources in a specific sequence. When the checkpoint is going to happen, the before checkpoint method on those resources will be called in that order. So you define the order you want them to happen in, and that's the order they will happen in. When we do a restore, we reverse the order. So it's like going down a stack and then coming back up the other side. So we reverse the order so that you can do things in a described sequence. Gives predictable restoration of the important state. Does it work? So what we did here was we actually created like a proof of concept. You can download it from our website. And we said, okay, let's take a couple of simple applications, run it on OpenJDK, look at how long it takes to get to first transaction, and then do a checkpoint on it and see how long it takes to do first transaction using restore. Spring Boot. So we took, I think it was probably the pet store application, and we ran it on a particular machine that took, let's say, 4 seconds, 3,898 milliseconds to get to first transaction. When we did a restore, we got first transaction in 38 milliseconds, 2 orders of magnitude faster. And remember, all of the code, all of the warm-up has already happened. So you're running at full speed with all the data that you need immediately available. Same thing with Micronaut, we did that. Okay, 1 second versus 46 milliseconds, still pretty much 2 orders of magnitude. Same with Quarkus, 980 versus 33 milliseconds. So it's interesting to see that this is actually working. And in fact, the Spring people have now integrated this into Spring Boot, so you can use it if you want to with the CRaC enabled JDK. Just to summarize then, I think it's fair to say that there isn't one solution that fits all situations. So if we look at things like ahead of time compilation, Graal VM, That works very well where you want fast startup, small footprint, ephemeral services, those types of things. Ready Now and Project Leiden provides memory of the JIT compilation across runs. Our cloud native compiler can offload the JIT workload from the JVM itself to a centralized resource, enabling us to do more heavy optimizations, store state, and optimize that way. Ready Now Orchestrator combines basic Ready Now and the cloud native compiler, and then CRaC gives you the ability to restart the application from a known point where you don't just have the JIT compiled code, you also have all of the state, all of the information in your heap readily available, and you can go from that point. Project Leiden, as I said, is looking at similar approaches to include all these, plus some other ideas as well. So that is the end of my presentation. So I'm going to stop sharing and come back.
I want to say thank you. We have a lot of thanks in the chat. So thank you very much for great and insightful presentation. Really nice to see that Leiden project is like still in place, and a lot of stuff is happening there. And also, that ahead of time compilation, JIT compilation is also like still with us. So that's really great one. So questions. First one was from Denise. When you talk about ahead of time compilation and that we need to store somewhere this information, like which we like have in the first start. So where is the profile information persisted? Let's say I have EKS cluster with pods running Java application, so there is no permanent storage for the pod, only a ephemeral one.
Right. So if we're talking about ahead of time compilation, as in Graal VM, then what you would do is you make this part of your CI/CD pipeline, and you would actually run a test version of the application, generate the profile for that test, and then feed that back into the compilation. So there isn't any need to persist that data beyond the profile guided optimization. For the things like Ready Now that we do with our product, we store those in like an S3 bucket and make that available through the cloud, so that you can just pull that from wherever you need to. So it's configured when you start the JVM as to where the information comes from. So we can persist that in different ways.
Okay, thanks for the answer. Next question was from Tatiana. Simon, thanks for the great speech. Are there any existing implementations or applications of the cloud native compiler approach from cloud providers, for example, in their serverless computation services?
Right. No, because this is something that we've been working on as a separate project, as a separate product. So we have customers that are using that for their environment, but I don't believe there's anybody that's offering that as part of a cloud implementation yet. I mean, we are working with AWS on some other things. So maybe at some point we'll be able to offer this as an AWS service so that people can take advantage of it.
Well, this would be really exciting. Another one from Igor. Thank you for a great presentation. What specific performance metrics should developers monitor to assess the effectiveness of JIT compilation in their applications?
Yes, always a good question. Realistically, what you need to look at is throughput, because JIT compilation is all going to be about throughput. So it's essentially, if you're talking about, let's take Kafka as an example, transactions per second. So Cassandra as well, things like that. You're looking at transactions per second. With other applications where it's like maybe an application you've written yourself, it's about figuring out what are the performance metrics that you need to measure. So it could be response time for how quickly you can respond to a particular request from something, or however your application works. But it's one of those kind of open-ended questions. So depending on what the application is doing, you need to look at what you need to measure to understand what the performance benefits are in terms of it. But it's essentially throughput. So we're not talking about latency. Latency is garbage collector. But for JIT compilation, it's all about how many instructions we can, or how quickly we can do the work of the application.
Okay, thank you. And I think the last one from my side. When you mentioned the let's say, cloud compiler, it reminds me that somewhere like 4 or 5 years ago, there was some advertisement on the market, I think from Eclipse Foundation and from IntelliJ, that IDE would be in the cloud. So we would do everything in the
Yes.
cloud. It will be shared. We can connect to the CD from mobiles, from iPads, whatever. Well, we are not there. I haven't heard about that for now. So, what do you think? In your opinion, would it be the same with this cloud compiler, or is it more like more long term, and we will really see cloud compilers everywhere?
I think it definitely has more potential, I suppose, I would say, because as you say, with things like IDEs, there's this idea that you can really just have a sort of interface to your IDE, and the work of the IDE can be done in the cloud. But most people want to run the IDE locally on their laptop because that's the way that people do development work. But with the cloud native compiler, because we're running so many workloads in the cloud, it's something that makes a lot of sense from the point of view of saying, okay, well, let's not do all of the work locally in the JVM. Let's shift it into a centralized service so that we can have a memory of code that's been compiled before. We can dedicate more resources to it, spend longer doing background compilation, things like that. So as I say, we've got some fairly large customers who are using this very effectively. And it's something that we're still continuing to develop. So at some point in the future, like I say, maybe we'll be able to get this as a service that we can offer through AWS or Azure, so that people can use it in a more general way.
Well, that would be really fantastic. So I think that's it from our side. Simon, thank you very much for this great talk. It's always a pleasure to have you on our conferences. Thank you very much.
Thank you so much. I was really glad that I was able to sort this out, because I had a few problems because I'm in South Africa at the moment, and I know that you were very accommodating with my timings. So thank you so much for that.
Thank you. That's great that we were able to find the slot. Thank you very much. See you on future Java Ons. Thank you very much.